Performance optimization tips. Physics in Unity. Physics is an integral part of many games. As game developers, we often use physics to model reality or check when things collide. When you start thinking about the code structure of your project and planning your design, learning how physics simulation affects performance will help you avoid running into issues later on in your production. In this video, we'll go through some of the key physics considerations to keep in mind when you're aiming for maximum performance. These tips will help you stay within the target frame rate while you're progressing from a prototype to a more complex project. To learn more about physics best practices and to get an overview of the physics systems in Unity, visit the links in the description below. Physics simulation frequency. First of all, consider how often you need to run the physics simulation. Physics engines work by running on a fixed time step. This means that the time between each physics step is exactly the same as the previous step. By default, Unity runs the physics simulation at 50 Hz, which is the equivalent to 50 frames per second. To view the fixed rate that the project is currently running at, go to Edit, Project Settings, Time. The field Fixed Time Step shows how long it takes to update between each interval. A value of 0.02 is equivalent to an update rate of 50 Hz. To change the update interval to 60 Hz, we divide 1 with our target frame rate, which would give us the time step of approximately 0.01667. While 50 Hz is the default, you generally don't want physics to run multiple times per frame. For example, if the game logic ends up running for approximately 35 milliseconds, the physics step will run twice, as 2 simulations are required. More physics steps means more work is needed to compute the simulation. So it's important to set the fixed time step to be a value that is appropriate for our game. If our game runs at 60 Hz, having our physics step run at 50 Hz means that generally we'll perform 1 physics step per update. On lower-end devices, it's possible to run into what is sometimes called the physics spiral of doom. This occurs when our variable update loop takes too long to run, and then multiple physics steps are needed to run to match the length of the long update loop. In this case, the main update loop and the physics update loop struggle to sync with one another, performing wasted calculations and costing performance. Simulating manually. We can also simulate our physics step manually by invoking physics.simulate. For example, if our game has a large spike due to a heavy load, we can manually simulate our physics step such that it aligns more with the performance state of our game. This allows us to have a situation-bound physics step, if in the event we ever need it. This also sidesteps having the physics engine trying to simultaneously perform multiple unneeded updates and causing performance issues in cases where we can predict that that may happen. Colliders. Colliders are the basis for defining the shape properties of our objects in the physics simulation. We can define our physics shape to be a primitive, such as a cube, a sphere, or a capsule, or we can define a unique mesh to be the shape of our rendered object. Preparing data for mesh colliders. Physics engines usually run in 2 major steps, the broad phase and the narrow phase. The broad phase collects potential collisions that can happen, and this data is sent to the narrow phase, such that the collisions are actually computed. When generating runtime meshes to use in the mesh collider, it's important that generated meshes have properly created triangles. Meshes required by the physics engine will usually go through a process known as cooking, which is a process that optimally builds the spatial structures for physics queries. It's best to set the cooking options to produce faster results if you properly created a mesh with no degenerate triangles. To do so, you can disable options such as Enable Mesh Cleaning, Weld Co-located Vertices, and Cook for faster simulation. As of Unity 2019.3, there's a new option known as the Fast Midphase option that skips generating resource-intensive art trees that were dominating the cooking time for meshes. By default, this option is enabled for all new projects. Additionally, mesh cooking can be offloaded to another thread using the C# job system. To cook meshes on a different thread, you can create an iJob parallel for job, create a native array of instance IDs, and pass the number of meshes to operate per job. In our BakeMesh job, we simply read the native array of mesh IDs and call physics.bakemesh. Box pruning for large scenes. The physics engine works in two major steps, the broad phase and the narrow phase. The broad phase attempts to efficiently determine the number of collisions which are needed for the narrow phase. If you have many colliders, then there are more potential collisions to check. Unity's physics engine uses a sweep and prune approach, which can generate false positive collision pairs on generally flat worlds with many colliders in it. To reduce the number of false positives, you can switch the broad phase type from sweep and prune broad phase to automatic box pruning. This option can be found in Edit, Project Settings, Physics, Broad Phase Type. Automatic box pruning is similar to multi-box pruning, except that it automatically determines the world boundaries and the number of grid cells in the world. Disabling automatic transform syncing. When a transform is updated, the transform is not automatically pushed to the physics engine. Transformation changes are accumulated to an array that is synced to the physics engine when needed. By enabling the physics.autosync transform to true, a sync point is then added before every query from the physics engine. This can lead to a loss of performance if the transform component changes and then you perform physics queries such as raycasts in quick succession. By default, since Unity 2017.2, physics.autosync transforms is disabled for all new projects. Colliders and rigid bodies. While colliders generally define the shape of the body, rigid bodies register the body to be influenced by Unity's physics engine. Reuse the collision class instance. Unity exposes callback events in monobehaviors such as onCollisionEnter, onCollisionStay, and onCollisionExit. These callbacks generally have a collision instance as a parameter, which is allocated on a managed heap. Because the collision instances are allocated on the managed heap, they'll be collected by the garbage collector, which can degrade performance. To reduce the amount of garbage collected, you can enable physics.reuse collision callbacks. This will ensure that each callback invoked will receive a single instance of a collision pair. You generally would only need to disable this option if the collision object is referenced outside of the collision callbacks for post-processing. Moving static colliders. Static colliders are generally considered game objects with a collider component and do not have a rigid body in their hierarchy. In early versions of Unity, prior to Unity 5, it was not advised to move static colliders because this regenerated the spatial tree for the broad phase. Versions newer than Unity 5 optimize the spatial tree rebuild for 3D physics. In 2D physics, it's still not generally a great idea to move a static collider, as the tree rebuild is still time-consuming. Also, it's not a great idea to add a rigid body component to a static collider for the sole purpose of moving a physics body if all you intend to do is query against it. Instead, you can translate the position of the physics body and allow the physics engine to accumulate the positional changes during its physics step. If the physics body will interact in a more complex way, it should still have a kinematic rigid body. When moving a kinematic rigid body, internally the physics engine will compute a velocity such that the rigid body moves over time during the physics step. As such, you should only add a kinematic rigid body if it is the behavior that you need for the game. They are not needed for simply moving objects without complex physics behaviors. Using per-body solver iterations. Sometimes, we may need to have a more accurate simulation. Instead of increasing the simulation frequency by manipulating fixed delta time steps, we can increase the number of solver iterations per rigid body. You can access the solver iterations variable from a given rigid body and set a custom value. This variable overrides the global default solver iterations static variable, which can be inspected in Edit, Project Settings, Physics, Default Solver Iterations. Adjusting the per rigid body solver iterations is generally fast, since it's only applying additional computations to a single rigid body instance, rather than all rigid bodies in the simulation. Raycasts and queries. Raycasts and other physics queries, like overlap sphere or boxcast, allow us to detect and collect colliders within a certain distance and direction. Use non-allocating queries. Any physics queries which return multiple instances of objects will allocate these objects on a managed heap. This means that the garbage collector will eventually collect the allocated objects, which can decrease performance if it happens at the wrong time. To reduce the overhead of this, it's generally recommended to use the non-alloc versions instead. For example, if you use an overlap sphere to collect all potential elements around a point, it's better to use an overlap sphere non-alloc call instead. This allows you to create a fixed size array of colliders to store all queried colliders into. The function finishes executing when there are no more colliders to collect, or if the number of collected colliders reach the size of the buffer. For example, if we create an array of 10 colliders, and there are 11 colliders around our point, we would collect 10 out of the 11. Therefore, it's advisable to allocate a fixed size that is large enough for the situation you expect to encounter in the game. Use batch queries. Running queries immediately is very convenient when writing code. However, there are some downsides to this. If you tend to have many colliders in the scene, computing these queries on the spot may contribute to a significant amount of time being used to query. There is an advanced option if you have a situation where you need to query a large number of colliders. You can perform a batch query instead. Batch queries use Unity's C# job system, and you can access this option through the Raycast command API. To use the Raycast command, we allocate a native array of Raycast hits and a native array of Raycast commands. The Raycast commands will store the origin, the direction, the collision layers to take into account, and the number of max colliders the ray accounts for. We call raycastcommand.scheduleBatch and pass in our native arrays of Raycast commands and Raycast hits, the amount of work done per job, and a job handle, such that the scheduled job knows when to run. If you don't need the query done immediately, you can follow the concept of scheduling the job early and completing the job late. This means you can complete the job by the start of the next frame by calling jobhandle.complete. Physics can create intricate gameplay, but has a performance cost. When we know these costs, we can tweak our physics behaviors to manage these costs appropriately and reduce any performance degradation that may occur. To learn more physics optimization tips, we highly recommend looking at the Physics Best Practices page on Unity Learn and through the Unity manual linked in the description box below. Thanks for watching.